backscattering communication and wireless power transfer. And she will be presenting the work that she conducted last year during her postdoc at MIT with the Signal Kinetics group. So let's welcome Aline. Good?
Yeah. Okay. Let's just make sure. I'm not sure this is working. It is? Oh, is it? Okay, well, that's not working. That's fine. Hi, everyone. Thank you so much for being here. I'm very excited to tell you about the research and progress we have made in the field of ocean IoT. So with that, I'd like to start asking a question. What plays the largest role in the world's climate? Well, it seems that the animation is running on its own. I was going to ask if it's CO2 or food, but it's actually the ocean. So the ocean over the last few decades, has absorbed more than 90% of the heat content that has been generated in the atmosphere. It holds more than 93% of the CO2 of the entire planet, and it covers more than 70% of this planet. So with the ocean being that important, the question is, how much of the ocean have we observed? Or maybe let me ask the question in a different way. What percentage of the ocean has never been observed? The answer is very shocking. More than 95% of the ocean has never been observed, which means that we are missing more than 95% of the data to form these optimized climate models. So how can we observe the ocean at scale? What can we do about that? Well, one way to do that is to deploy sensors, for example, at depth of hundreds of meters, and then you can have that ship on the surface of the water, and then communicating with these sensors and collecting information. Building ocean IoT has a lot of very, very important applications, such as in climate monitoring, in aquaculture or seafood farming, and ocean exploration, and a lot more than that. So how can we build an ocean IoT? What are today's approaches? Well, first, some approaches are using classical acoustic modems. For those of you who are unfamiliar with communications underwater, you can not use Wi-Fi or Bluetooth because these signals do not propagate well underwater. So we use acoustic signals. Now, the problem with these approaches is that they consume a lot of power. So imagine that you put these sensors in the water and you have to go down, replace these batteries, which is extremely expensive and also impractical. So our group has developed over the last years what we call underwater backscatter. So this is here what I'm showing is the acoustic transducers or piezoelectric transducers that we've been using to do backscatter communications. It has been used for underwater localization, bringing advances in machine learning, underwater, very recently also building battery-free camera to do underwater imaging as well. Now, what is amazing about underwater backscatter is that it actually consumes 1 million times less power compared to traditional approaches. But we have a problem. The problem is existing underwater backscatter architectures can only achieve few to tens of meters in range, which makes them very difficult to deploy at scale, such as the example I gave before, right? Putting them at hundreds of meters of depth. So the solution I want to discuss today is bringing this new backscatter technology underwater that extends the range and the coverage of communication. And I'm sorry about the running animation. So let's start to understand first why the current range is limited, why underwater backscatter cannot achieve long ranges. Well, first let me explain how backscatter works. Generally, we know that we have a transmitter, a receiver, and these two are communicating with each other. But now, backscatter communications works this way. You have the transmitter sending that signal towards what we call a backscatter node. And now the backscatter node is not actually generating a signal. All it's doing is reflecting that energy back to where it came from. But in that case, it's reflecting it in all directions, which means that the signal is being wasted in undesired directions. So what is the new approach? The new approach is retrodirectivity. Retrodirectivity means now you have your transmitter sending the signal towards your node, but now the node, instead of sending back that signal in all directions, it's focusing it exactly to where it came from. So with the focusing of energy, we will be able to achieve all the results that we're about to talk about today. So the contributions here are, this is the first ever retrodirective backscatter to be implemented underwater. It achieves 15x range improvement compared to the ART, and it has been, the entire system end-to-end has been implemented and evaluated over 1,500 real-world experimental trials in the river and the Atlantic Ocean. So how did we do that? Well, to achieve this retrodirectivity, means focused beams back to the receiver, we leveraged the concept of Van Attas. So Van Atta structures are structures that are known in the RF radio frequency community. And the way it works, the way you can achieve this retrodirectivity, is by building an array such as I'm showing right here. So to make that array, you have to connect it in that way while you have your nodes, and your nodes are like a car's battery. They have plus and minus. You put them together in an array, and you connect the plus plus, minus to minus, you make them into pairs, and you achieve retroreflectivity. This is great. But the important question here is, how do you encode data? For simplicity, let's take the unit cell, 2 elements. To encode data in backscatter, what you do is you put a switch in between. We talked before about that reflection that comes back from the node. And what you want is you want to modulate that reflection so the receiver sees 2 different states. Now, if we take the case of this switch that is opening and closing, in the first case, we have a switch closed. The signal arrives to one node, goes to the other node, gets reflected. Same thing happens on the other side. Node 2 receives, node 1 reflects. So this is our bit 0. Let's look at bit 1. The switch is open. The signal is received now by both nodes, and then what's going to happen, because the switch is open, it'll get reflected back to the source. So if you look at these 2 scenarios, you will notice that bit 0 and bit 1 look very similar at the receiver. You're getting reflections in both states, and thus you cannot decode. So how can we solve this? What we've done here is we kept bit 0 the same, switch is closed, plus plus, minus minus connected to each other. And then we introduced cross-polarity switching. So what we did now, instead of connecting plus to plus, we connect plus to minus to send bit 1. You can see now the signal goes, it goes into the other node to the minus polarity, and it gets reflected as a minus signal. And same thing happens on the other side. And now, by getting 2 very different reflections, you not only maintain retrodirectivity in both bits at 0 and 1, you also achieve states that are very differentiated back at the receiver, and that's what you want. Now, of course, this was one of the problems that we solved, but there were a lot of different problems that I cannot really dive into here, but I just want to mention that connecting the nodes like this to each other doesn't work. You detune the operation of the nodes, and you need a certain matching network to enable the maximum power transfer from one node to the other. So that's where we designed a transformer-based matching network to enable maximum power transfer. Something else is, as you make this array and you start rotating the structure to measure it at different angles, one node starts occluding the other. And to resolve that, we introduced staggering, where we elevated one node with respect to the other to mitigate that problem. Here I want to show you quickly our implementation and evaluation. This is our final Van Atta array, which is 4x2 element. Of course, we tested multiple sizes of the array, 1x2, 1x4, 2x4, etc. These are our TX and RX arrays with all the boards that we designed in order to do the matching, the amplification. And finally, here we have our evaluation dock, where we did all our measurements here at the Charles River, where we had the reader placed at one location, and we're moving the Van Atta in range in order to test its performance. This dock is 155 meters in length. So here what I'm showing you is the result of our BR, bit error rate, with respect to range of the baseline and the Van Atta. Now, the baseline is the current ART, what we have achieved so far with underwater backscatter. And you can see that the BR increases from 2e-2 to 0.5, where it cannot really decode anymore, anywhere beyond 10 meters. But with our Van Atta structure, you can see actually that we're able to decode beyond 150 meters. So with that, our Van Atta achieved 15x range improvement compared to the previous ART. Now, if you're interested in that, in the paper, we have done a lot more experiments in terms of different switching techniques and antenna architectures, switching architectures, retrodirective versus not retrodirective throughputs, power levels, etc. With that, I'd like to end and reiterate on the fact that this is the first ever retrodirective structure with 15x range improvement. But what we're very excited about is that even the structure achieved the over 300 meter round trip we were really limited with the size of the dock. And with some of the, one paper upcoming, a Mobicom paper, we did the end-to-end link budget analysis to show that with this system, you can actually achieve theoretically kilometer scale ranges. And we implemented this with 1,500 real experimental trials at the river and the Atlantic Ocean. So I want to end by saying that what started actually here at SIGCOMM' a few years ago as this very exciting intellectual idea of making communications a lot less power, what we're doing here is we're making it more practical by extending the range of communications. With that, I'd like to end, and thank you so much for listening. I'm happy to take any questions.
Any questions from the audience?
I have one question. I think it does, right? There are different properties, I think, Jack. So the salt or fresh water make a difference. Well, we did test it in the river and the ocean, and I think the river is fresh water, and I don't think we saw a lot of difference in the results, so I don't think so. Okay, we have.
Great talk. You mentioned that we can only observe, I forget what %, but like a very small. So you improve the range at which we can sense now. Do you have like an updated number or just a sense of how much further range you need to boost that observability up?
Yeah, well, a scenario that we have in mind is not, you don't really have to achieve these thousands of kilometers. With achieving these hundreds of meters, you can imagine a scenario where you deploy these sensors at the bottom of the ocean or at hundreds of meter depth, and then you can have a ship that has the reader on it and go on top of the surface and communicate with all these sensors. So the deployment, in our opinion, can start with even hundreds of meters of range.
Thank you, Aline. So next, we're going to have our second talk, which is enabling ubiquitous Wi-Fi sensing with beamforming reports. And the presenter is Chenhao Wu. Chenhao is a PhD student in the Chinese University of Hong Kong, and his research interest is in wireless networks. So, Chenhao.
Thanks for the introduction. I'm Chenhao, a PhD student at the Chinese University of Hong Kong. Today, I'm excited to present our work enabling ubiquitous Wi-Fi sensing with beamforming reports. This is a joint work with Xuan Huang, Professor Jun Huang, and my advisor, Professor Guoliang Xing. A major breakthrough in recent wireless system research is to use Wi-Fi signals for ubiquitous sensing. And by analyzing the ubiquitous Wi-Fi signals in the environment, we can achieve a broad range of applications like localizing the physical objects, recognizing the gesture of human, and so on. Wi-Fi sensing is expected to be a major technology for ubiquitous sensing because today Wi-Fi is almost everywhere. If you Google Wi-Fi sensing, you'll notice the number of papers in this topic is almost doubling every 2 years. This exponential growth indicates the increased interest and rapid advances in this field. The magic of Wi-Fi sensing comes from the channel state information available on community devices. And as many other wireless systems, Wi-Fi signals broadcast through multiple paths in the environment, and CSI contains the information of all these paths, which allows the system to detect the variations caused by things like human motions or even breathing in proximity. And unfortunately, to realize the vision of ubiquitous sensing on Wi-Fi, the key challenge here is that CSI measurement is actually not available on most of today's Wi-Fi devices. As a matter of fact, only several legacy Wi-Fi chipsets offers the interface to extract CSI, which still requires some hacks to the firmware. To this reason, although that despite numbers of amount of research in all these years, Wi-Fi sensing has not yet found its way into the devices that we currently use. In this work, we aim to address this limitation and bring sensing capability to currently deployed Wi-Fi devices. The opportunity here is that many operational Wi-Fi devices support a feature called transmit beamforming. We found that a special Wi-Fi frame, which is initially used to support transmit beamforming, can be used for sensing purposes. The frame is called the Compressed Beamforming Report CBR frame. CBR frame carries essential information for beamforming, and utilizing CBR frame for sensing offers us two key advantages. First, it is widely supported among commercial devices, especially for newer devices. And second, CBR frames can be easily sniffed in the wireless traffic. To validate our basic idea, we need to first answer the question of how many Wi-Fi devices today support this new Wi-Fi sensing scheme. We have conducted a urban scale measurement study in Hong Kong. Our approach is to analyze the Wi-Fi frame sent from operational Wi-Fi devices at different locations and use these frames to fingerprint the radio capability of these devices. And in our measurement study, we found that the number of devices that support existing CSI tools is extremely limited, less than 6%. And in contrary, we found that over 73% of newer Wi-Fi devices support CBR. This indicates that the CBR-based sensing is indeed widely supported and has the potential for enabling truly ubiquitous Wi-Fi sensing capabilities. So to utilize the CBR for sensing, let's first understand how the 3D matrices is generated in CBR. So the 3D matrices is basically computed from the singular value decomposition of the channel state, and only the right matrix V is remained after the decomposition, and then the 3D matrices is further compressed with coordinated rotation and quantization. And all this process reduce the information from V and are not invertible. So the key message here is that CBR essentially is a lossy transformation of CSI. And as a consequence, compared to CSI, the CBR is significantly less robust to various dynamic channel factors. Therefore, machine learning models trained based on the CBR are difficult to generalize to new devices or different environments. And instead of using machine learning models, can we use like a first principle physics-based models? Unfortunately, this is also not possible. This is because the CBR frame only contains partial channel information, and therefore there's no existing first principle model to interpret CBR. So in summary, directly applying CBR for sensing is actually not a good idea. So now we have seen that existing models cannot use CBR no matter they are first principle based or the machine learning based. So can we reconstruct CSI from CBR? If we can do so, we can keep all the advantages of CSI while still being compatible with most of operational Wi-Fi devices. This task seems to be very challenging. This is because SVD is a one-way factorization, and there has no closed-form solution to reverse CBR into the CSI. So a natural way to handle this problem would be like you design the maximum likelihood estimation, and a naive solution would be like iterate over each CSI candidate and use singular value decomposition to generate CBR and compare the generated CBR with the sniff CBR. And among these candidates, we can select the CSI that produce the closest result. This approach, however, has significant computational overhead in practice. This is because there are too many candidates to examine, and the computational overhead to compute singular value decomposition is too large. So to address these challenges, let's revisit the basic of multipath channel modeling. The wireless channel of Wi-Fi can be modeled as the aggregated result of physical paths in the channel, and each path can be described by angle of arrival, angle of departure, attenuation, and path delay. And instead of searching the high-dimensional CSI, if we can estimate these propagation parameters, we can essentially reconstruct the multipath channel to know which multipath profile is desired. So here we, instead of regenerating the CBR for evaluation, here we leverage the channel fingerprints in bidirectional CBR. So to understand how we construct the evaluation function, let's first recall the SVD of the channel. The SVD decomposes the wireless channel into 3 different parts: the input space, output space, and the power gain of each subspace. And the beams in each subspace are essentially the fingerprints of the channel. First, the candidate channel is expected to be nullified by unpaired steering vectors. And for paired vectors, the candidate channel is expected to constrained by ASNR. And leveraging these fingerprints, we construct an efficient MOE evaluation. And so compared with regenerating CBR for evaluation, which requires multiple times of SVD, our approach only requires several times of matrix multiplication, which greatly reduces the computation overhead. And we also employ 2 optimization strategies to accelerate the searching process. And in our paper, we also present several approaches to improve the estimation accuracy, like mitigating the hardware errors. So put it all together, we design BeamSense, an anti-pinning layer between CBR frames and the CSI-reliant applications. So at a high level, BeamSense sniffs the bidirectional CBR frames from Wi-Fi link and use these frames to reconstruct the channel state information. And BeamSense addresses the limitation of CBR and allows seamless migration of CSI-reliant applications to use CBR as a new sensing source. We implemented BeamSense and conducted an extensive evaluation. So our experiment aims to answer the question that can BeamSense perform as well as CSI. So we have tested 3 popular Wi-Fi sensing applications, and the first application is to localize the Wi-Fi device. So the figure shows the accuracy of the device localization application based on raw CSI. And if we switch to CBR, you can see that the performance is just dropped a little bit. And this result is also found in the application that passive tracks the human trajectory. And lastly, let's see some results that use Wi-Fi devices to perform gesture recognition. And we test on a data set of nearly 300 different gestures in 2 different environments. So the first result is that directly applying the CBR frame produces the worst results, while BeamSense can achieve a similar performance as of using a raw CSI. So in conclusion, compared to CSI, CBR is widely supported among operational Wi-Fi devices. And in this paper, we present the first system for ubiquitous sensing, and we evaluated on 3 popular Wi-Fi sensing applications, and the result shows that CBR is able to perform a similar performance as of CSI. Thanks for listening. I'm happy to take questions.
I'm Haofan from UCLA. My question is, can you briefly explain what's bidirectional CBR versus ordinary CBR?
Bidirectional CBR is like you have uplink CBR and downlink CBR, and ordinary CBR only have downlink CBR. So bidirectional CBR, in a bidirectional CBR, you can have the channel fingerprints used to perform the multipath estimation. Yeah.
Hi, my name's, over here. Hi, my name is John Drogo with Columbia. You mentioned a little bit about how the CSI frames are typically not being used by current generation modem systems and Wi-Fi networks. For the CBR frames that you observed, did you see any correlation with particular manufacturers or protocols that were exposing the CBR frames? As in, do we expect CBR support to get better over the next few years?
Yeah, CBR frame is actually supported since AO211N, and as in our measurement study, we found that many of today's AO211AC or AX devices will support the CBR frame, CBR frames to support transmit beamforming, and we expect this ratio will increase in the future. Yeah.
Thanks for the nice talk, Fadel Adib, MIT. Very cool work. Two questions. What is the part of the signal in the CBR that matters specifically in, is there a specific bandwidth that you need in order for this to work? And as part of this is, what other spectrums would this extend to? Like, would it work with some of the 5G or 6G, other areas of the spectrum as a method?
Yes. Okay. Our work is working like a conventional Wi-Fi spectrum, like a sub-6 GHz Wi-Fi spectrum, and we evaluated our performance using 20 megahertz, 40 megahertz, and 80 megahertz, and even like larger bandwidth. And we think that this technique can be applied in like other wireless technology like 5G, because in both systems, the wireless devices need to do beamforming, and also people use them for sensing purposes. So I think there's an opportunity of combining these technologies. Yeah. Thank you.
So when I set up, I will introduce you. So our next talk is underwater 3D positioning on smart devices, and the presenter is Tuochao Chen. Tuochao is a second-year PhD student in computer science at University of Washington. Outside of underwater networking, his main interest is in mobile intelligence and enable superhuman hearing on smart devices. So Tuochao will be presenting using different software. So. Let's see. It's fine. It's here. It's here. So present. Oh, good.
Hey everyone. My name is Tuochao Chen. Today I will talk about how we can bring the underwater GPS on the smart devices. And in just the last year, both Apple and the government have introduced new underwater mobile technologies. For example, the Apple Watch Ultra design for waterproof up to 40 meters, and they can precisely check the depth of the diver. So these new smart devices open up opportunities for underwater networking and positioning. In last year's SIGCOMM', we demonstrated that by using the microphone and the speaker on the smart devices, we can enable the underwater messaging. So this year, we're asking the following question: can we enable the underwater 3D positioning on the smart devices? So let's dig a little deeper why we care about underwater positioning. In a diving activity, for the safety reason, it is very important for the dive leader to know the positions of the dive members. And this will get extremely challenging when the visibility is limited and the separation between the diver increases. So let's look at in-air GPS. So in-air GPS works almost everywhere on Earth, but unfortunately fails on the waters. This is because the satellite signal cannot easily penetrate the water and can attenuate very quickly. So let's take a look at the existing positioning system for the underwater robot. It turns out they're using dedicated and expensive anchor infrastructures. Specifically, this anchor using acoustic signal to localize, and they are deployed in a fixed location to triangulate the position of the underwater robot. However, this anchor deployment requires complex setups, and this overhead is a bit excessive for the activity of diving. So here's our contribution. We first proposed the first underwater 3D positioning system for the smart devices. And using our devices, the dive leader can localize all divers without any anchor infrastructure. We also evaluate our system in various underwater scenarios and show promising localization accuracies. So now let me introduce how our system works. So our main intuition is that in a well-connected networks, if we can compute the pairwise distances, then we can determine the topology shapes. For example, here are 3 nodes, A, B, and C. Let's say A is the leader. He wants to know the position of B and C. If A can measure the distance to B and C using acoustic signals like this, if the position is finished, the answer is no. because B and C can still rotate around the A, and A cannot uniquely determine the position of B and C. But you can still measure the distance between B and C. Now the entire topology will be fixed, and A can acquire the positions. So our intuition is that if even if without any anchor infrastructure, if we can measure the pairwise distances among enough number of nodes, we can still determine the topology and the relative positions. However, to do this in practice, we need to solve 3 key challenges. The first challenge is the error measurements in this pairwise distance. So in our system, we leverage the speaker and the microphone to sharing the audio messaging among different devices to measure the time of flight, which result in the pairwise distances. However, in underwater scenario, it's very special because there might be very severe multipath and possible blocking of direct paths, which may lead to very large distance measure errors. The problem is that these errors in pairwise distance can drastically change the topology estimation. Here, for example, here is actual topology for 5 nodes. Let's say if the distance measurement between nodes 1 and node 2 have a large error, as shown in the red line. Then, if you try to estimate the topologies with this wrong estimation, you can see the output topology will drastically change. It looks very different. So our solution is that we design an iterative algorithm to detect the outlier distance measurement by using the objective function as shown below. Specifically, when we compute the topologies, if we find their objective function is very high, above a acceptable threshold, then there might be some outlier measurements happen here. So we iteratively drop the links. For example, we drop the link between 1 and 5 here, and we compute the topologies. Since 1 and 5 is not the erroneous links, so the objective function is still very high. Let's say if we drop the link between 1 and 2, and we compute the topology, we can say the objective function will drastically decreases, and then we detect, so this might outliers. We know that we limit the outlier number to maximum to 3 for algorithm complexity and stabilities. However, the second challenge is that the topology is fundamentally not sufficient for positioning due to the rotation ambiguities. Given a topology here, you can see the diver's position is still not determined because they can rotate along the axis of the leaders. So we need to determine which angle of this diver it is. So our solution is a human-in-loop solutions. Specifically, the leader will point his smart devices to a nearby diver, and the digital compass on the devices will record its current orientation. Then we can rotate the entire topologies until the corresponding edge aligns with the pointing lines. So in this way, by assuming the leader can see just one diver, then the rotation ambiguity can be solved. However, we have not done yet because we still cannot get the unique positions because the flipping ambiguities, which is the mirror image position as shown in the dotted line here. So we need to determine which of these 2 mirror image position is the actual position of the divers. So our solution is to leverage the 2 microphone, which is very common on the current smart devices. For example, this diver is a green point which on the right of this device. When he sends signal, the signal will arrive at the right microphone first. So if the diver on the left, and which is the mirror image, when he sends the signal will arrive at the left microphone first. Based on this high-level idea, we design a joint maximum likelihood estimator to resolve the flipping ambiguity. So we varied our positioning system in 5 different underwater scenarios with cheap Android devices, as shown in the image. And in our evaluation, the median positioning errors was 0.8 meter and 0.9 meter for 4 to 5 device networks with low network latencies. And our system can still work with reasonable mobilities, missing links, and blockings. Finally, our free-pin resolving algorithm can increase the accuracy when the device number increases. So to conclude, we present the first underwater 3D positioning system on the smart devices. Let's take a step back. So we also find that revisiting the distributed anchor-free positioning, which was proposed in 2000, can still be useful for practical mobile systems. And finally, some human-in-loop design can help solve some technical problems. For example, in our scenario is the Ubiquitous solutions, which might otherwise be very challenging. Okay, so thank you for your listening. So I'm happy to take any questions.
Hello, great talk. I'm Purey from MIT. So I have a question that what is the typical SNR for the mobile devices like Apple Watch when you measure from underwater, and how do you to support what kind of typical working range do you need? A specific signal processing or accumulation, or how long is the pulse being repeated or averaged to get a reasonable SNR for a reliable distance measurement?
Okay, thank you for questions. So there are several questions I need just to answer one by one. So the first question for the SNR measurement, we do a lot of measurements in 10 meter, 20 meter, 30 meter, and 40 meters. And it shows that, the underwater is very noisy, and we're using the audible spectrogram on the smartphones and smartwatch to play. And we find that for the Android smartphones, for some frequency band, the SNR for some frequency band can arrive at 10 dB, 5 dB. So this is already sufficient for localizations. And the second question about is the signal duration design. So there's some trade-off for the preamble design. So the shorter preamble, which means we can give you low latency for your entire network and protocols. However, the smaller preamble, we also have just low SNR. So in our design, we consider this trade-off, and finally we're using some around 100 to 200 milliseconds preamble to transmit. And also the third question about the powers. We also have testing. We also consider the power drain on the smart devices, because you need to use this for your entire diving activities. So in our experiment, we just keep sending the signal, the preamble signal, in both the smartwatch and the smartphones, and show that it can support around 4 hours, which already very efficient, sufficient for the diving activities.
This is Tuochao Chen from University of Massachusetts Amherst. I have a question wondering, how do you choose the threshold for your objective functions? And have you or have you not observed a linear relationship between the threshold and the overall accuracy for positioning?
Okay, so when we talk about the outlier detection of the objective function, so what we do is we collect a bunch of data, and so empirically select the threshold, and also there are some, because when in underwater, the scenario is very special. It's not like in air, because the multipath difference, the length difference between multipath and repath is very large. It's just 20 meter or 30 meter, because you need to reflect from the bottom or the water surface. That will give very large errors. So we can easily detect this. So this one will give a large error, like the 10 meter, 20 meters in the entire object function. So the threshold we say is, I think is around just 5 meter, 2 meters. So, and this multipath, if you wrongly select the multipath, so the error will be very, very large, so it can be easily detected. Thank you.
So our next talk is a millimeter wave backscattering network, and the presenter is from Haofan Lu. Haofan Lu is a third-year PhD student in the computer science at UCLA, and he's interested in the integrated communication and sensing in IoT systems. And currently, Haofan is actively seeking internship opportunities for the upcoming summer, so if you are interested in his work, reach out to him. So, Haofan.
Okay, it's projecting. Okay. Good morning, everyone. I'm Haofan Lu from UCLA. I'm glad to be here to share with you our journey of developing a millimeter wave backscatter network for two-way communication and localization. This is a joint work with my colleagues, Mohammed, Reza, and me. The Internet of Things paradigm promises to connect everything together and will nurture a bunch of new applications, such as smart city, smart industry, and virtual reality. If we look at these emerging IoT applications, they have some common constraints or requirements. First, they all require high data rate communication to be able to deliver a huge amount of data. Second, they all require some sort of high resolution localization to be able to interact with people or environment. Last but not least, they usually have limited power supply and thus require low power consumption. Unfortunately, today's wireless systems has not yet been able to support these altogether. Luckily, there's a new technology called millimeter wave. Millimeter wave refers to radio wave of wavelengths at millimeter scale. There are orders of larger licensed and unlicensed bandwidths at millimeter wave frequency, which translates to much higher network throughput and high resolution localization capability. With millimeter wave technology, we can naturally satisfy the first two constraints, high data rate communication and high resolution localization. But how about the third one, low power consumption? The problem is, today's millimeter wave radios have very high power consumption. To solve this problem, researchers propose to use backscatter technique in millimeter wave communication. For those who are not familiar with backscatter, in a backscatter system, there's an AP, or reader, which tries to get data from a node device. The node device does not actively transmit radio signals. Instead, the AP sends a query signal. The node simply reflect or absorb the query signal to piggyback its data onto it. The AP can look at the signal reflected back from the node to decode the data. Because of this nature, the node design can be very simple and power efficient. There have been some pioneer attempts in millimeter wave backscatter, including our previous work, MMTag. However, all these previous works only support uplink communication only or localization only. None of them support downlink communication, which is also very important for IoT applications. Therefore, in this work, we asked the question, how can we design a millimeter wave backscatter system which supports both uplink and downlink communication as well as localization altogether? We proposed MILBAC, the first millimeter wave backscatter system which supports localization, orientation sensing, both uplink and downlink communication altogether. The key innovation of MILBAC lies in a novel beamforming technique and an orientation-assisted modulation scheme. We built a prototype of MILBAC and evaluated its performance in real-world scenarios. The first challenge in enabling MILBAC is to design a passive beamforming scheme. Let me explain what I mean. Because of the high-frequency nature, millimeter wave signals experience severe path loss as they propagate through air. To combat with path loss, we have to create narrow, pencil-like beams to concentrate energy. The AP and node can only talk to each other when their beams are aligned. Past work solved this problem using Vanetta array. As has been introduced in a previous talk today, Vanetta array is a retroreflective structure which can reflect the beam signal to its coming direction. Vanetta array creates a beam that is always pointing to the transmitter. However, the problem with Vanetta is that it does not have a port for receiving signal, and therefore we cannot use it for downlink communication. Our idea is to use frequency scanning antenna instead in millimeter wave backscatter communication. Frequency scanning antenna, or FSA, is also a passive structure which creates beams for signal of different frequencies towards different directions. We put the FSA on the IoT node. The good thing about FSA is that it has an RF port that can be used for receiving signal. However, using FSA also raises another problem. The beam is no longer naturally pointing to the AP, And therefore, the AP has to figure out the node's orientation to pick the right frequency for communication. This brings us to our second challenge, how to estimate the orientation of the node. To estimate the orientation, the AP sends a signal whose frequency sweeps across the whole bandwidth over time. For those who are not familiar with radar technology, this is the exact waveform used in many radars for localization. We use this waveform for both localization and orientation sensing of the node. So the AP sends this signal. It hits the node and gets reflected back to the AP. Because of the frequency-dependent beam pattern of the FSA, the signal gets stronger as the frequency corresponds to the orientation of the node. More specifically, if we plot the received signal power at the AP versus time or frequency, we get a plot like this. From this plot, we can accurately pinpoint the frequency corresponds to the peak power and identify the orientation of the node. So far, I have shown you how we enable beamforming and orientation sensing. Now, let's see how we can enable two-way communication on top of that. Our idea is to use the two-port FSA and an orientation-assisted modulation scheme, which we call OAQ-FM. Let me show you how we do it. An interesting fact about FSA is that it's actually a symmetric structure, which means we can easily add another port on the other side. In this way, we get two sets of beams overlapping on top of each other, and their frequencies are simply mirrored. In other words, each beam direction now corresponds to two frequencies. The node and AP can use these two frequencies for communication. And how can we do that? We developed a new modulation technique to encode bits on these two frequencies. Here, I'm showing you the constellation of modulation. Basically, we use the presence of these two frequencies to encode bits. For example, the presence of both F2 and F6 encodes bits 1, 1. Now, let's see how we can use this concept in both uplink and downlink communication. For downlink communication, the AP wants to send data to the node. Now, the AP has already estimated the orientation of the node, so it knows that F2 and F6 are the frequencies that align the beams, and it will use these two frequencies to communicate with the node. Let's say the AP wants to send bits 1, 0. It sends a single frequency at F6. And if the AP wants to send bits 1, 1, it sends both frequencies together. The signal gets split naturally by the FSA to two ports, so on and so forth. The node can simply look at the signal received at each port to decode the bits. Next, let's take a look at the uplink communication. Remember, we use backscatter technique for uplink. To do that, the AP will send a signal that consists of both frequency F2 and F6 continuously. The node depends on which bits it wants to send, either reflecting or absorbing each of these frequencies to encode bits on top of that. So far, I've shown you how MuBack works on the high level. Now let's take a look at the node design. Remember, we use a two-port FSA. We connect each port to a NAV switch. These two switches enable the node to either reflecting or absorbing signal. We connect each of the switch to a power detector for measuring the received signal power to decode the bits in downlink. Finally, we have a low-power microcontroller to control the switches and processing the data. As you can see, our node design is very simple, low power, and low cost. Now we present some of the evaluation results of MuBack. We built MuBack's node and AP using off-the-shelf components and evaluated its performance in indoor environments. First, I'm going to show you the downlink and uplink communication performance. First, I'm going to show the downlink performance when the data rate is 36 megabits per second. I'm showing you the SINR when the distance between versus distance between AP and node. As you can see, at 10 meters, our SINR is high enough to support bit error rate of 10 to the power of -8. We get similar results for uplink. Note that our data rate is actually limited by the speed of switches and power detectors. If we use faster switch and detectors, we can get higher data rate. Overall, MuBack supports both uplink and downlink communication. Now we show you some of the localization results. Okay, I'm going to show you the CDF of distance estimation over the distance estimation arrow. As you can see, the distance estimation arrow is mostly lower than 20 centimeters, which is very accurate. I'm also going to show you the CDF of the angle estimation error, which is limited almost within 2 degrees, which is also very accurate. So we can conclude that Mulback localized the node can very accurately. Finally, we are interested to see how power efficient is our node design comparing to previous millimeter wave backscatter systems and common wireless systems. As you can see, our power, I'm showing you the energy cost for delivering 1 bit of data. As you can see, Mulback power cost is way lower than BLE. And if we're comparing to MNTech, a previous millimeter wave backscatter system which only supports uplink communication, we are also doing better. Overall, Mulback has very low power consumption. To conclude, in this work, we propose Mulback, the first millimeter wave backscatter network which supports both uplink and downlink communication and the localization, also orientation sensing altogether. Thanks for listening, and I'm open to any question right now. Okay.
Hi, Jack Rademacher from MIT. Can you explain again how you combined the Atta with the FSA? How many elements do you have in the array?
Yeah, the fact is we don't use we don't use Atta at all. Instead, we use FSA to do the passive beamforming.
Okay,
yeah.
Thank you.
Hi, Aline, University of Michigan. I'm wondering if you can comment a bit on the range of the structure, like what would you do to scale it in terms of improving the range? Because I'm assuming if you compare it to the Atta, you might get less range in that regard. Is that correct?
Yes, our range is currently limited, but it's mainly limited by the insertion loss of all the components. We build this component using the evaluation board. They have some loss in the connection. If we build this node using integrate board, the performance can be much better. And we can also build a larger FSA to increase the range. Thank you.
Yeah, thanks to the speaker. So our final talk is about molecular networks, and this will be a recorded video. The video will be presented by the first author, Jiaming and Wang, who is a final year PhD student at UIUC. And for the Q&A session, we will have Saib Dawood, which is a second year PhD student at EPFL. So we will play the video, and Saib will answer the question. Is it playing? Okay. Okay, you can play. Okay. Let's play the video. So this is not clickable. Is that the video? Yep. Open it again. Where was it?
That one.
Where was the video?
Yeah, this one.
This one. What does this say? Okay. Play the YouTube version. Okay.
We're now going to look at a YouTube video.
SIGCOMM molecular. Yeah.
That one. Yes.
And we're playing it. Full screen.
Hello everyone, my name is Jiaming Wang. In this talk, I will tell you about our work towards practical and scalable molecular network. Nowadays, researchers are able to build micro and nano implants that can sit in the brain, travel through the bloodstreams to perform target drug delivery, all the way to contraception implants and lab-on-a-chips that can conduct in-body diagnosis. However, the question remains, how can we communicate and network such micro and nano implants? Traditional implants like cardiac defibrillators and pill caps use wireless, which may not be suitable. These wireless implants have a relatively large form factor. In some cases, they require an external device to power up. Besides, wireless signals does not propagate well inside the body. Instead, researchers have been turning into a new paradigm, molecular communication, which is inspired by the chemical signaling between cells inside the body, like the neurons release neurotransmitters or the glands releasing hormones. In its simplest form, an implant can transmit bits by releasing particles in the bloodstream, so releasing molecules for bit 1 and nothing for bit 0, which is similar to on-off keying. The molecules then travel along the blood flow and arrive at the receiver. Unfortunately, a lot of the work on molecular networking is still theoretical. There's very limited experimental work there. Researchers build testbeds to emulate the molecular channel, such as using acetylene-based salt molecules or magnetic particles. At the same time, there's also research in synthetic biology on building transmitters and receivers, but they do not focus on the communication channel. Considering this, we need more experimental research to understand how to build practical molecular networks. In our prior work, we focused on understanding the molecular channel. In particular, the channel is based on diffusion. If you focus on the released particles here in red, you can see that as they propagate, the color diffuses, the channel stretches, creating long tails and high intersymbol interference. We show that by accounting for the complexities in the channel, we can significantly improve the decoding for a single transmitter. But in today's paper, we ask, how do we scale the molecular network from a single transmitter to multiple transmitters? Past theoretical work proposes 3 types of media access protocols. The first is TDMA, which is great in theory because it avoids interference, but in practice, it requires synchronization. Let me tell you why synchronization is hard in molecular channel. As comparison, in wireless channel, the signal propagates at the speed of light, so it takes only 100 nanoseconds to travel 30 meters, making it easy to synchronize. However, for molecular channel, blood flow speed is only about 1 meter per second. Thus, it will take the signal 1 second to travel only 1 meter, where synchronization is much harder. But more importantly, is that unlike wireless, the molecular channel is asymmetric. Molecules cannot propagate back against the blood flow, so you do not get feedback from the receiver or a trigger to tell the transmitters to transmit. The second approach is molecule division multiple access, where each transmitter uses a different type of molecule. This would remind you of FDMA, but instead of different frequencies, we use different molecules. However, with this approach, you cannot scale because the receiver grows way more complicated to measure different types of molecules. And finally, there is CDMA, where we can use a code to avoid interference without needing synchronization. However, we cannot apply CDMA as is, since molecular signals are non-negative and have very high ISI. So, how do we design an efficient medium access protocol for molecular networks? In this work, we propose MoMA, Molecular Multiple Access, a practical and scalable protocol to enable molecular networking with multiple transmitters. Here are the key design principles of MoMA. First, we account for the unique channel properties, including high ISI, lack of feedback and synchronization, non-negative signals, etc. We customize CDMA codes for the molecular channel to allow us to separate different transmitters. In the meanwhile, we keep the transmitters as simple as possible. They can transmit anytime they have data. We just let them collide and push the complexity to the receiver. Thus, at the receiver end, we cannot nicely separate different functionalities like packet detection, channel estimation, and decoding. We'll have to do them jointly and iteratively. Later, I'll tell you about the importance of packet detection, which were overlooked by previous work. And finally, we show that you can improve the performance by using 2 or even more types of molecules. I won't have time to go over everything, so I'll focus only on 2 ideas. First, let me tell you why packet detection is so important. Without the synchronization among transmitters, the packets can arrive at any time. So while decoding, we'll have to keep checking if new packets arrive, which is very difficult when we're already dealing with other packets. If we miss a single packet, the bit error rate explodes for every packet on hand. Here's a result where we intentionally make 2, 3, or 4 transmitters collide. You can see that if we ever miss detecting a single packet, the BER goes from almost 0 to more than 30%. So why is it not easy to detect new packets? Prior theoretical work in molecular CDMA set the coded molecules for bit 1 and nothing for bit 0, resulting in the unstable concentration of molecules in data symbols. This is extremely problematic when another packet arrives and exactly fills the concentration gaps. Adding the higher intersymbol interference, it becomes very hard for the receiver to distinguish 2 transmitters from just 1 transmitter sending bit 1s. So what does MoMA do? We make sure that the pattern in preamble is very different from data symbols. First, instead of sending nothing for bit 0, MoMA sends the complementary code, so the molecule concentration in data symbols becomes balanced across time. For the preamble, however, we do the opposite. We repeat the chip once back to back to repeat large fluctuations in concentration, which allows us to more easily detect new packets. Let me show you how the signal looks like in an experiment when you do this. You can see that although the 2 signals share equal average concentration, the blue preamble changes way more drastically than the yellow data. And as a result, the new packets can be easily told from the increased signal power as well as its fluctuations. Another highlight is how MoMA makes better use of multiple molecules. Suppose we have 4 transmitters and 2 molecules in the system. What you could do is to divide the 4 transmitters into 2 groups, and the first group uses molecule A, while the other uses molecule B. Then you can use CDMA within each group to separate the transmitters. Using this scheme, naming molecule division CDMA, you would reduce interference by half. But what MoMA does is to have all transmitters use both molecules. Feel confused? Although this idea might be counterintuitive at first glance, because collisions are still there. But there are more advantages. First, MoMA can send independent streams of data on different molecules. Thus, you can use longer code while keeping the same data rate. But remember, longer code means much lower bit error rates. More importantly, you can achieve much better channel estimation and packet detection. Remember, we're saying how important packet detection is. The longer code plus individual preambles on each molecule means much more samples for these 2 procedures. This turns out to be way more important than just reducing collisions. Let me show you some results. MoMA is evaluated on an emulated testbed built with pumps and tubes. The evaluation includes 2 different topologies, the long one and the fork one. The dataset also includes 2 different molecules, which are the table salt and baking soda. We compare MoMA with the baseline molecular division CDMA, which was explained a few slides ago. The network has 4 transmitters and 2 molecules, while the data rate per transmitter are the same for both protocols. We can see that when there are only 1 or 2 colliding packets, it does not really matter. But when it comes to 3 or 4 colliding packets, MoMA achieves 70% higher throughput than the baseline, and it is only 10% loss compared to the data rate. There are much more results in the paper, but in the interest of time, let me conclude here. First, molecular networks are essential for communicating with micro and nano implants. Second, we propose MoMA, which is a MAC protocol that can scale to multiple molecules while keeping the transmitters as simple as possible. But in the meanwhile, it also has several limitations, like it is only uplink and assumes a complex receiver. But for future work, we do need a lot more networking research in this field. We need to rethink and redesign our networking protocols while working closely with biologists and bioroboticists. For more details, please refer to our paper and artifacts. Thank you.
I'm happy to take questions.
Hi, Jack again. I'm wondering if you've looked into ways to, it seems like the blood and fluid channel is so harsh, it's so high delay, it's a lot of ISI. Is there any way to like piggyback off of the signals that our neurons use, like without being invasive in any way? Have you looked into that at all?
So
there is some work on synthetic biology where these experts engineer bacteria to use actual living cells to do molecular communication, but our work is on the networking side, so we haven't looked at that. Yes?
Hello, very great talk and very impressive improvement on the protocol. So I'm Purey from MIT again. Can you comment on like the equivalent of the interference and like ambient noise in this molecular channel, especially if you will be deploying that in human body? I suppose there will be some environment chemicals that are essential to the to the body, and that could and your communication would also like release those chemicals, and that could also be potentially harmful for the body. And like how do we solve these problems to make your communication and the patient themselves more better?
Okay, thank you. In our testbed, we don't use any harmful molecule. We have used salt and baking soda, but however, this is a good point, and this should be elaborated on future work, but our testbed is not harmful. Thank you.
Ahmed Alam from MIT. Great talk. I was wondering what types of data that can you communicate, or you typically communicate using molecular networks, and the typical data rate that you need to collect them. And also a follow-up, where would the receiver be, and how would you extract this data to the outside world?
Okay, so to answer the first question, since we have a setup with multiple transmitters and multiple molecules, we have different data rates, but with a single transmitter and a single molecule, we obtain around 1 bits per second data rate. And the other question was, I guess, how this receiver performs, but it runs through the blood as with the blood flow. So
yeah, but how do you
dynamic.
extract it to the outside world? Like,
yeah, okay. Right now we have a macro scale testbed, and we don't operate on the micro scale one, but this field is on its first steps, and hopefully in the future the situation you're talking about would be researched as well.
Great, thank you.
All right, so we wanted to have mini panels at the end of each session where the speakers could ask questions of each other, or we could ask questions of the session as a whole. We are running a little late, but we do have an hour and a half for lunch. So I would like to ask the speakers to go on up and ask one another a question. Or does anybody have one or two questions for the session as a whole? This is perfect. Thank you all so much. Any questions for the session? I have one. Which medium do you think is the most fun to work in?
I think I can help you answer a wrong answer. I think water is not a happiest medium, because during my experiment, I'm just in Seattle. During the winters, I go outside, test a whole bunch of the on the what scenario. It's cold, windy. So I think on the water is very hard and different to do. Yeah.
Any disagreements?
No, I was actually going to agree. So I worked in air and in water, and I decided to pursue as a group, as a faculty, in air. So I'm not going back to water.
I feel air is more fun because it's invisible. Like, it's amazing you can do all of sensing and communicating things with, but you cannot actually visually see it. So it's so amazing to me.
And I think blood is the most fun one, as it's very new and exciting. And yeah, that's.
And it's the grossest. All right.